Hi guys. So even though I'm not there today, I wanted to try to help us not fall even further behind by teaching you section 6.1. I'm going to do the best that I can to teach this to you as if I was there. So this requires your patience and your attention and just overall participation in learning this lesson. So first thing I'm going to do, this is section 6.1. I know we're going backwards, but I don't want to get into the nitty-gritty things until after Christmas break. Okay. So what we're going to do is we're going to review a construction that we did called the perpendicular bisector of a segment. Okay. So I'm going to switch to a different screen right now to review that construction with you. So that construction, if you remember, hopefully this is not too blurry. Okay. It's probably a little blurry, but it's enough for what we're going to do. Okay, for this construction, we've done it like 1,000 times. If I want the perpendicular bisector of a segment, we take our point of our compass, put it on one end, open more than halfway, and we make an arc on top, arc on bottom. Same setting, come to the other end point, make an arc on top, make an arc on the bottom. Mark those 2 points of intersection. And then you take your straight edge and you draw the line connecting those 2 points. And that is the perpendicular bisector of the segment. And remember, as a bonus, BOGO, buy one, get one, you get the midpoint. And that point is equidistant from the endpoints of the segment, because that's what a midpoint is. It's a point on the segment that's equidistant from the endpoints. But the new thing that we're doing is that not only is the midpoint equidistant from the endpoints of the segment, but something interesting happens with any other point that is on this perpendicular bisector. And that's what I'm going to show you now. Okay, so I'm going to switch screens again. Now I'm going to take you real quick to Geometer's Sketchpad. So hopefully you're able to see my Geometer's Sketchpad screen. And notice here, it just so happens, oops, wrong screen, sorry. This is the perpendicular bisector screen. Here I have a segment, and I'm going to go ahead and use Geometer's Sketchpad to construct the perpendicular bisector. So given this random segment, first I'm going to make a midpoint, the midpoint of the segment rather, and then I'm going to highlight the segment and the midpoint and construct a perpendicular line. I'm going to make it a different color so it stands out from the original segment. So this is the perpendicular bisector of the segment. And if I go ahead and I measure this distance from here to here, the distance is 4.84. Okay, and if I measure the distance from C to the other end, it's going to be 4.84 as well. So as it always is, the midpoint is equidistant from the endpoints. But as I mentioned earlier, if I pick any other point on this perpendicular bisector and measure its distance from the endpoints, I'm going to actually make a little segment there, construct a little segment. Let's make it dotted. And then I'm going to make one over here as well. So if you look at those two segments and I measure the distance from each of those endpoints back to D, if I measure those lengths, notice that it's 7.57 here and 7.57 here. Okay, let me go ahead and move this point somewhere else. Notice that each time, as long as the point stays on the perpendicular bisector, it is equidistant from the endpoints of the segment, just like the midpoint is. Notice that as I get closer to the midpoint, this distance gets smaller and smaller. When I actually reach the midpoint, it's at its smallest distance. And as I move it away, it gets further again. I want to make sure you understand this only works. It's only equidistant from the endpoints of the segment if it's on the perpendicular bisector. It just so happens that I have another one here, okay, that I have the segments drawn in as well, but I have some hidden and I want to show to you over here. Here I have point X. Notice that point X is not on the perpendicular bisector. It's not on the red line. And look at the distance from A to X and the distance from X to B. Okay, I'm going to highlight them so they stand out. It's not the same distance from each of the endpoints because X is not on the perpendicular bisector. So I did want to point that out. So with that in mind, now we can go to our theorem. And our theorem for this says both are true both ways. If a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints. The converse is also true. If a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of the segment. So because it works both ways, these can be combined as a biconditional. So now with that, let's go ahead and do some sample problems. These are from your book, from this section of section 6.1. To be exact, if you open your book with me, these would be on page 486. So let's go ahead and look at these examples. Okay, so let's look at this figure. We're going to start with number 3. Okay, example 3. Line ZX, they're telling you, is the perpendicular bisector of segment WY. Okay, so they're telling us that this is the perpendicular bisector. We need to know that before we can apply this theorem. So that tells us that Z is going to be equidistant from the endpoints, okay? And they want us to find the length from Y to Z, given that, they're giving us the length from Y to Z, though the length from Y to Z is 13.75, and they want us to find the distance from W to Z. They want us to find this. So as we mentioned earlier, it has to be equidistant. Z has to be equidistant from the endpoints. So this would be 13.75 as well. So the answer for this one is 13.75. Please take a moment to make the ticks in your book. Mark the picture. Okay, so now we're going to go on to number 4. Same concept. Okay, we're going to erase all this and we're going to start from scratch. We do know that XZ is the perpendicular bisector as mentioned earlier. Okay, it's going to be equidistant from the endpoints. Z is going to be equidistant from the endpoints. And now they're telling us that the distance from W to Z is 4n minus 13. And the distance from Y to Z is n plus 17. And they want us to find the distance from Y to Z. Well, remember, if these are both equidistant, then you would set these two quantities equal to each other. 4n minus 13 would be equal to n plus 17. Now we're going to solve for n. Move the n over. So we're going to have 3n minus 13 equals 17. Now we're going to add 13 to both sides. Please excuse my sloppy handwriting. I'm writing on a vertical surface. It's not that simple right now with the angle of my hand. Anyway, we get n equals 10. And that's it. We're done. Psych, we're not done. Because they want us to find the distance from Y to Z. So we have to go back and plug in here. So since the distance from Y to Z is n plus 17, we just found out that n is 10. 10 plus 17 is 27. And that is the answer for number 4. So I'll give you a second to write that down. You can pause the video if you like. Let's verify that. It tells you here that they want you to find WX. They do tell you that this is 20.5 and that this is 20.5. So because both of those are the same, that means that Z must lie on the perpendicular bisector of the segment. So these two pieces then are the same. We're using the converse now of the theorem we were given earlier. So again, if we know that all of this is 14.8, and we just said right now that this must be the perpendicular bisector, to get what they're asking for, which is WX, you would take 14.8 and divide it by 2, and you would have 7.4. And there you go. That's your answer for number 5. I'll give you a second to write this in, and when you're done, just pause the video. I'm sorry, to pause the video, and then when you're done, press play. Okay, so now what we're going to do is we're going to talk about a different kind of bisector, which is an angle bisector. Okay, so I'm going to stop this share and start a new share with my camera again. So going to the camera, let me remind you about the angle bisector construction that we reviewed last week again. So now we're cutting an angle in half. So again, the way that this construction worked is you put your point on the vertex, okay? And you can swing one continuous arc, again, open your compass to any setting, or just make an arc that crosses one side and then the other side. And then you mark those 2 points of intersection. And you can use the same setting, put your point on one of the intersection points, make an arc inside the angle. With the same setting, go to the other one, make an arc inside the angle. Again, you don't need to do this construction. I just want to review it with you. Mark this point of intersection and draw the ray from the vertex through that point. So once again, that is the angle bisector. Okay, angle bisector. So I wanted to review that construction with you. Another construction that I wanted to review with you before we proceed is the perpendicular to a line through a point that is not on the line. Again, we reviewed this last week. So the way this construction works is we know that there's infinitely many perpendicular lines that I can make on this paper, but only one that passes through that point. So the way we did this construction is we put our point here, opened it a little bit past the line, swing an arc that crosses in 2 places, mark those 2 places, put your point on one, open more than halfway to the other one, make an arc on the bottom of the line since you already have a point on top. With the same setting, go to the other intersection point, make an arc on the bottom of the line. Mark that point of intersection, draw the line through both of them. So understand, I want you to be clear. This is the perpendicular bisector. I'm sorry, this is the perpendicular to a line through a point that was not on the line. But I mentioned once to you that if you're trying to find the shortest distance from a point to a line, you would use the same construction. I believe I used the airplane example. If an airplane is flying at a certain altitude and the pilot says that you're 30,000 feet above the ground, the pilot is talking about the perpendicular path. So if you're ever trying to find the shortest distance from a point to a straight object, it would be along the perpendicular path. That would be the shortest distance. We did that once before earlier in the year. So I wanted to review those things. So now that we did that, what I like to do is I want to go back to Geometer's Sketchpad, and I'm going to give you a plane angle bisector. Here it is. A plane angle, I'm sorry, and I'm going to construct the angle bisector. Okay, I want to make this a solid line, and I want to make it in red. That way it'll be easier to see. Okay, so this is the angle bisector. And let me hide these points here, B and C, because we don't need these, and I think these might cause confusion. Okay, so here I have an angle bisector. I do want to put a point on the angle bisector. Here it is. Let's call it D. Okay, now what I'd like to do is I'd like to measure the distance from D to this side and from D to this side. Okay, now the way that I measure distance, from a point to a straight object, like I mentioned earlier, is along the perpendicular path. So I'm going to make a perpendicular from D to this side. Okay, you don't have to do this. I just wanted to show you. Okay, this would be a perpendicular line, but all that I need is where it hits that. So I'm going to focus on these two, and I'm going to make a segment, and I'm going to hide everything else because I don't need everything else, and I think that's going to confuse you. Okay, so this would be the distance that I would measure from D to this side. Measure length, it's 4.03. If I make a perpendicular distance from D to this side, again, I don't need the whole thing. I just need to know where it crosses. And I make a segment there, measure that segment, and hide the rest. I have a lot going on here, but I just want you to focus on these two perpendicular distances. Notice that they're the same. Even if I move D further away from the vertex or closer to the vertex, okay, D is equidistant from both sides. If a point is on the bisector of an angle, it is equidistant from both sides. I'm going to say that again. If a point lies on the bisector of an angle, it is equidistant, and I mean the perpendicular distance is the same to both sides. Okay. Now I want to make sure I point something out to you that a lot of kids get confused. Here I have some other scenarios that I want to show you. Okay. Let me make this a little bit darker because this light green is very difficult to see. Okay, so notice that here I have point P. Point P is on the bisector of this angle. Notice how these two distances are the same. Even if I were to move it further away, they are the same, okay? Because the perpendicular distance to each side is the same. But notice I went from P to point C, this orange segment, and then I went to the other orange segment, and those lengths are here. This is 9.23. This is 10.02. Why aren't these orange segment lengths the same? Because you have to go along the perpendicular path. This is not perpendicular to this side. This is not perpendicular to this side either, only the perpendicular path. Even if P is on the angle bisector, it has to be the perpendicular path. That's why these were not the same. The homework is going to try to trick you. Don't be fooled. It's only the point that's on the angle bisector, and it's only the perpendicular distance that's the same. Now notice how here I have a point G. Okay, I did do a perpendicular distance here, and it's 1.56. I did a perpendicular distance to the other side. Why aren't these the same? Because G is not on the red angle bisector. If I try to get it closer to it, they'll get closer to each other. It's hard to get it perfect. Okay, freehand. Okay, they're getting closer to each other. There it is. Now they're the same because G is on the angle bisector. But if I move it away, it doesn't matter that I'm going along a perpendicular path. They won't be the same. So again, if a point is on the bisector of an angle, then its perpendicular distance to each side of the angle will be the same. Let's go ahead and look at the theorems. So here are the two theorems in the book. Okay, again, if a point lies on the bisector of an angle, then it's equidistant from the two sides. And again, I'm going to emphasize this, the perpendicular distance. So notice how they have to say it's the perpendicular distance. That perpendicular distance will be the same only if we're talking about the angle bisector. And this red line, ray rather, is the angle bisector. And how do we know that? Because they tell us, and we also know that by the ticks here. Okay, the converse is also true. If you have a point that you suspect is on the angle bisector, and you see that it is equidistant from the sides, then it is on the angle bisector. So with that in mind, let's go to some examples here. And these examples are in your book on page 488. Okay, so the first one, here we have B. They're telling us that BD bisects angle ABC. B is the vertex, D is on the angle bisector. They're telling us the distance from A to D is 3Z plus 7, so we're going to mark that. And the distance from C to D is 2Z plus 11. So we're going to mark that also, and they want us to find the distance from C to D. Again, these have to be equal to each other. These distances have to be equal to each other. So we would set 3Z plus 7 equal to 2Z plus 11 and solve for Z. So we would have Z plus 7 equals 11. Now we're going to move the 7 over to the other side. Sorry for the mess. Z equals 4. Am I done? Nope. They asked me for the distance from C to D, which again, the distance from C to D they gave us was 2Z plus 11, but Z is 4. Okay, so it's going to be 2 times 4, which is 8 plus 11, or 19. So that's the answer for the first one. So go ahead and write that down. Pause the video if you need to. Okay, so now the last one, we're starting from scratch now. On the last one, I'm going to erase all this. Okay, the last one that we're doing, find the measure of ABC. So they want to know this entire measure. That's angle ABC. Okay, given that the distance from A to D is 3.2, the distance from C to D is also 3.2. So here we see that it's equidistant from both sides, which means that this must be the angle bisector. So if they tell me that the measure of angle DBC is 39, DBC, that angle there measures 39 degrees, then the one up above it would also measure 39 degrees. So the entire angle would be 39 times 2, or 78 degrees. So the answer for this, the measure of angle ABC, is 78 degrees. So hopefully, guys, this lesson in summary, if a point is on the perpendicular bisector of a segment, going back to the first theorem, it is going to be equidistant from the endpoints of the segment. And the converse, if a point is equidistant from the endpoints of a segment, it must lie on the perpendicular bisector of the segment. If a point lies on the angle bisector, on the bisector of an angle, it's equidistant from the sides. The perpendicular distance to the sides is the same. And the converse, if a point is equidistant from the sides of an angle, it must lie on the bisector of the angle. So with that in mind, now you can do the homework that's on the board, which is section 6.1. And I hope you enjoyed this video.